for introduction, and hello everyone. So today I will focus on the high availability levels and how they affect your system architecture. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. Before I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings, but on a daily basis, I'm an engineer. A few words about Hazelcast. So Hazelcast is it is a distributed company. We produce distributed software. Our products are Hazelcast IMDG, Hazelcast Jet, and Hazelcast Cloud, which is Hazelcast as a service. We are also a distributed company in a sense that we all work remotely from all over the world. Our engineering team is mainly located in Europe, but we all work remotely. So we are good with what came now. Now everyone works remotely, but we used to do it before the coronavirus. Our agenda for today is pretty simple. So we will walk through all high availability levels that you can use in your system. And I will always mention how it affects your architecture of your system. And while I will be speaking, I would like you to focus on two things, or to ask two questions to yourself. One would be your system on which high availability level is located. So is it multi-instance, is it multi-zone, multi-region? And the second question is, would it be easy for your system to upgrade to one level higher? Or would it require a lot of architectural changes? And with this questions, I leave you to listen to this talk. So the introduction. So in the center of every system, there is always a service. So sometimes we call it a microservice. Sometimes we call it a microservice, even though it's actually a macro service. But it doesn't matter if it's a microservice, macroservice, is it even a Lambda function that you run on a serverless environment. What matters is that this service is something stateless. Something stateless things are very simple in IT. So something, just imagine that all your system is just a bunch of stateless services. So just imagine that you build a system like with the services, with only services like a calculator that adds two numbers, then you don't have any problems with high availability. Because you can deploy this calculator service on your laptop, you can deploy it in the cloud, anywhere, it always works the same. No problem with high availability at all. However, the IT world doesn't look like that. You always have a service which is connected to some stateful items like a data store or a queue, or it uses some other service, internal or external. So actually, the problem in the context of high availability, the biggest problem is the data. So that is why in this talk, I will mostly focus on the data part, on databases. As an example, I will always give an example with Hazelcast, which is an in-memory data store, but it applies to any stateful thing in your system. So let's move to the level 0 single instance. So single instance means no high availability at all. So basically you run everything on one machine. You run your service, you run your data store. So the flow is as follows. A request goes to our service, which is located on our machine. Service uses some database, which is also located in our machine. So as simple as that. You can think of this as like the normal development environment, like running everything on your laptop. That is this environment. So you may think like, what kind of developer, what kind of YOLO developer would use this kind of high availability? But remember that not every system needs to be highly available. Like for example, like idempotent batch job, which you can repeat anytime you want. It doesn't require to be highly available, so you can run it on a single instance. What is good about single instance that the latency is low. I did a latency experiment running Hazelcast on my machine and a service which was doing like read writes, and I measured the latency of one read write, and for the 10,000 of entries I had like a result of 80 millisecond, which may not tell us much, but we'll compare it later to the other high availability levels and see how it's different. So what does single instance mean to you? Single instance, we are not highly available at all. There is no scalability, but on the other hand, you have super low latency and your data is always consistent. And this consistency is something we will lose while we are going up with the high availability levels. So let's move to the multi-instance. So multi-instance means that if one machine is down, your system is still available. A diagram for this would look like that. So we have requests going to our system. There is a load balancer, which load balances the traffic to application services. These application services are located obviously on different machines, and they use data store, which is also located on at least 2 machines. On this diagram, there is only one thing that is single, which is load balancer. However, the thing about load balancer is that this problem is kind of solved. You can use some DNS-based load balancing, and the load balancers are also very reliable. So we will not focus much on the load balancer. Also, as mentioned earlier, application services are super easy to make highly available because they are stateless. So we will not focus on them. We'll focus on the data. So our assumptions here are that we have our data store on at least 2 machines. The network between them is fast and reliable. As an example, we could start just 2 EC2 instances on AWS and run 2 database instances. In reality, like this local network is usually like a data center. So this is a photo actually from the data center from CERN in Geneva. By the way, if you happen to be in Geneva, you should go there. You can go for a free tour and see not only the data center, but like even way more interesting stuff like all these colliders and everything. It's really super interesting. So we have 2 database instances located on 2 machines, and now we have to solve like a problem of data replication. And what I will tell you now is like short story of data replication. So they're like usually with the SQL databases, when this was a standard like SQL databases, they supported like active passive replication or master slave. So the idea was that application services used they use only one instance of the database, and the second instance is either passive or it's read only. Now, when something bad happens to the machine 1, if it crashes, then we have a failover. So application services start to use the machine 2, and that's how we cover the failovers. Now, that was the standard, but still that is actually still a standard for most relational databases. That's how it works. But together when the NoSQL databases emerged, they said we need something better. Like we need something better in terms of performance, in terms of resilience. So most NoSQL databases, they use clustering. Clustering means that application services, they use all the instances of the database, and each of the instance stores part of the data. So the data is partitioned somehow, and they use all the instances, and each instance stores part of the data, and the backups of this part of the data is stored on other instances. Then if one machine is down, then we restore the backup data and we don't lose any data. So to give to go a little deep into how it works, so let me give you an example from Hazelcast. So this is exactly how it works in Hazelcast. So if we have three what we call members, which is like three instances of Hazelcast, then the data is partitioned, and each member stores part of the partitions. Like member 1 stores here partition 1, 4, and 7. Now the backups of this partition 1, 4, 7, they are located on member 2 and 3, or on one of the members 2 or 3. And the rule here is that always the backup needs to be stored on another member, so that when member 1 is down, we can always restore the data partition backups and promote them, migrate the partitions, and don't lose any data. What we do by default, we always store one backup of the partition, but obviously you can configure this, because if we store one backup of each partition, it means that if one member is down at the same time, we don't experience data loss. However, if two members are down at the same time, you can experience data loss, but this is configurable. So that is actually how most NoSQL databases work these days in terms of the data replication. Now, the question that that may arise is, should we do this partitioning backups, the backups of the partition, should it be an asynchronous or synchronous operation? In other words, should we favor like consistency, meaning we are synchronous, or should we favor latency, meaning that we do the backups asynchronously? And would it matter if we are doing like active-passive replication, or we are doing clustering? Will it be any different? And before I answer this question, I did another like latency experiment. And this time I started 3 Hazelcast instances on 3 machines and measure again like read-write operations. And I did it with synchronous backup, and that was the result. So it may look, the latency may look high comparing to the single instance. However, actually it's like 3,000 milliseconds per 10,000 of entries. So one read-write is still under 1 millisecond, which is usually still acceptable. And that is why in most cases with the clustering, you will use synchronous backups, because you want this data consistent. Obviously, you can configure this, but that will be the default behavior in most NoSQL databases. Now, will it be the same for SQL databases and this active-passive replication? Not necessarily, because like in this databases, this backup operation is usually it takes more time. That is why, for example, MySQL by default they use asynchronous replication, but you can obviously configure this. Short summary: what multi-instance means to you. So you have your data. You can still achieve data consistency, which is super important. Most tools support it. You can use a lot of cloud-specific toolkit, like for queuing, you can use AWS SQS, and most tools they support it. And the setup is very simple, even if you would like to run on premises, like Hazelcast on your infrastructure or Hazelcast on AWS. The setup is pretty simple. From the downsides, you are located in your one local network. So if you access your system from any other region, or the latency will be high. Okay, let's move forward. So we go from multi-instance to multi-zone. So multi-zone, what it means is that if one availability zone is down, your system is still available. An availability zone is usually a few data centers in one location. And the point of availability zone is they always have a separate power supply, and all this infrastructure is separate, so that if there is no power, it affects only one availability zone, not two. So usually, like availability zone, you will see on the cloud environments, they are usually in the same, like even city, but on the other parts of the city with the separate power supply and all the infrastructure. This one, by the way, this photo is a data center and availability zone from Facebook. So the diagram for multi-zone looks like that. Request goes again to the load balancer, which load balances the traffic across application services, which are located on the machines located in at least two availability zones. And the same with the database is located on the machines in at least two availability zones. So you may look at this diagram and say, like, you know, it looks pretty similar to the diagram like multi-instance. So is the multi-zone deployment any different? Is there any different than multi-instance? So I would say, like, no, it's not much different, but yes, there are some differences. So let me first start with this no. So why it's similar? So I did another latency experiment for multi-zone, and obviously latency is higher for multi-zone than multi-instance, but it's not way higher. It's still one entry is still under 1 millisecond, which is usually acceptable. And the result like this is because if you take like cloud provider like AWS, they have a dedicated infrastructure between dedicated connection, the internet between availability zones. So it doesn't go through any public infrastructure, and also it's not far away from each other, these availability zones. That is why latency is not way higher than multi-instance. But I mentioned that there are some differences between multi-instance and multi-zone. And to explain these differences, let's look at this diagram again. So imagine that you have like 4 instances of a database. It can be a Hazelcast, for example, and these machines are located in 2 availability zones. Network is obviously fast and reliable between them. So you can, just to replicate this this example, you can start like 2 EC2 instances in one availability zone and 2 EC2 instances in another availability zone, and form one cluster. So if you remember like this diagram from Hazelcast, you remember that the rule was that the partition backup is always stored on another member, which makes sense. So if one member is down, we don't lose data. However, it may happen that one partition is located on member 1 and the backup of this partition is located on member 2. However, they are located in the same availability zone. Then if zone 1 is down, we lose the data, and it's obviously not something we can afford. That is why, like, we thought how to solve this problem, that we would like to be high available in terms of the multi-zone with Hazelcast, but how to achieve it. And we came up with the idea of the zone aware feature. So that is how we enable this in Hazelcast. So you, with the simple setup, you say, okay, the Hazelcast should be aware of the zones. And now how to get the information about the zone, because the high availability zone is something cloud specific, so it's different in AWS, it's different on Azure, it's different in GCP or in Kubernetes in general. So we came up with the idea of the plugins. They are also used for discovery, but we also use them for fetching the zone in which the given member is located. And like that, if you run Hazelcast on AWS, Hazelcast instance will query, using this plugin, it will query the AWS API asking, okay, in which zone I am located. And then the Hazelcast cluster knows how to locate each partition backups, so that in the result, the backup of the given partition is located always in a different availability zone. That is why I said like that it's not different, but it's that it's multi-zone is not different from multi-instance, but it's still, there is some difference. You have to make sure that your data store is zone aware. And that is and you cannot take it for granted, because it's not every tool supports zone aware feature. So it's something you have to really take into consideration while choosing the right tool. So what does multi-zone mean to you? So I would say it's currently the top one choice. So most software works this way, because you are super high available, but you can still keep the data consistency. And you can use a lot of cloud-specific toolkit like AWS SQS, for example, they support. From the downsides, obviously, you need to make sure your tool is zone aware, and you are still located in one region, meaning that if someone accesses your software from some other regions, the latency will be high. We go from multi-zone to multi-region. So multi-region, it means that if one region is down, the system is still available. The diagram would look like that. So we have now a geo-load balancer, which takes your location, your geolocation takes into account when it load balances the traffic. And then in each region, we have separate load balancer, we have application services and data store. And between like data store clusters for each region, there needs to be some replication, which we call a geo-replication. So the assumption here is we have machines in at least 2 geographical regions, and the network may be slow and unreliable. It often go even through the public internet, the traffic between regions. Now you may wonder, like, what's the big deal about these regions? Why is it so different? So the thing is that the regions are like physically they are far away from each other. Like if you take like these are the regions for GCP, and if you take like even Finland and Oregon, you will see that like there is 10,000 kilometers in between. And 10,000 kilometers, it means like even if we calculate check the speed of light in a vacuum and calculate the round trip time, we'll see that it's 60 milliseconds just for the light to go there and back from Finland to Oregon and back. And this is in a vacuum. In a fiber, it will be even like 3 times at least more. And then you have to count all these routers, all this public infrastructure. So it goes really bad. It goes to the point that you just cannot use it like synchronously. Then that you need like a geo-replication. And geo-replication is basically like replicating the data between clusters, between data clusters in a different geographical regions. Now, what is special about geo-replication? So the first thing is the clusters are far from each other. So the replication needs to be asynchronous. This is one thing. Your data store must support it, which again, you cannot take it for granted because your data store may support it or may not support it. And since this is asynchronous, you must be prepared for the data loss. And for the geo-replication, usually you will see 2 modes. One is active passive, meaning we write only to one cluster, and the receiver, the passive cluster, it's either not used or it's read only. Now with this, you have to be prepared for the data loss because we do the replication asynchronously. So you might have written something to the active cluster, it may be down all of a sudden, and the data was not replicated yet. So you must be prepared for the eventual consistency. With the active geo-replication, it's even worse because you still need to be prepared for the data loss and eventual consistency, but now you have to be also prepared for the conflict resolution. Because what happens if you change the same value at the same time in 2 different clusters? And what to do, the choice is not obvious because it may depend on your business logic. So your application business logic must decide on that. And like in Hazelcast, we provide like policies, like you can choose like the simplest policy you can imagine is like first one wins or the last one wins, but you can have some custom policy. And some other databases, I think like Couchbase, they, for example, keep always the whole tree of the conflicts and the application needs to resolve it always. So this is not a trivial question how to resolve conflicts in the databases. In Hazelcast, if you would like to, we call this geo-replication, we call it WAN replication. If you would like to configure this, it's pretty simple. You just configure Hazelcast WAN replication and say, where should I publish the data? And that's it. So you just give the IP address. Obviously, there you can configure much more things, like the size of the batch, etc. But the simplest configuration would be just saying, okay, I would like to replicate my data to a cluster which is available under this IP address. That's it. But you may wonder, like, my system is very important. Do I really need to lose the consistency? And I did like a latency experiment again. And I did something I shouldn't do. I created a Hazelcast cluster, a synchronous Hazelcast cluster across different regions. And I measured the latency. What would happen if I would like to keep the data consistent across different geo-regions? And that was the result. So you can see like the latency was super high. It was not a little higher than multi-zone. And at this point of latency, it's just not acceptable. It will be just not usable by normal use case. Obviously, like for a geo-replication, so if we do this asynchronously, this will be the same as the multi-zone because we do the replication asynchronously. Now the thing, this is what you see on this plot. That is the reason why you cannot have, for example, Kubernetes cluster across multiple geographical regions. because Kubernetes inside it uses etcd data store, which needs to replicate the data, which needs to be across different instances, and it needs to do it synchronously. That is why you cannot split your Kubernetes cluster across multiple regions. So if you go to the GCP, you can create a Kubernetes cluster across multiple availability zones. No problem with that. That is a very good approach actually, but you will never have like a Kubernetes cluster across multiple geographical regions. If you really need strong consistency in multi-regions, I encourage you to read about NoSQL databases, like from Spanner from Google, or the open source version of the Spanner, which is CockroachDB. They do a lot of tricks, like they have like very well synchronized clocks, so they can and they also have consensus algorithms, so they can agree on some value. But if you would like to keep something in sync, it's always a trade-off between consistency and latency. Short summary of multi-region. So what does it mean to you? So if you use multi-region, you are super high available. You can achieve low latency if your system is accessed from multiple regions. And it's sometimes possible to use cloud-specific toolkit like the Google Spanner supported, but not everything supports it. So like you take AWS Elastic Cache, it does not support. From the downsides, you have to use geo-replication, which means that you have to be prepared for asynchronous replication, which implies eventual consistency, call-free resolutions, and all these things we mentioned. Okay, let's move from multi-region to multi-cloud. So multi-cloud means that if one cloud provider is down, your system is still available. That is how it looks like. So we have like a global load balancer, which load balances the traffic across different cloud providers. And in each cloud provider, we have basically the clone of your whole system, and the data store is replicating the data. So as an assumption, we have machines in at least 2 cloud providers. The network may be slow and unreliable, and the machines can be in different geographical regions. So you may wonder, like, what's different from multi-cloud to multi-region? Are there any differences? And there are some differences. So you cannot longer use cloud-specific toolkit because each cloud is like you have AWS SQS, but on GCP you don't have it. You have a different solution for queuing. That is why you need to use your own tools, your own on-premise software. With the VPC peering, it's also, you don't have VPC peering across different cloud providers, which means that you have to think more about latency and security. So latency is usually worse across different cloud providers. And you also have to think more about security, because normally like VPC provides also the security for you in one cloud provider. And also in terms of cost, you will have to pay multiple vendors, so it usually costs a fortune. So one other thing you may wonder is high availability the only reason for multi-cloud? And obviously, no, it's not even the main reason. So the reasons for multi-cloud is, one of the main reasons is to avoid vendor lock-in, meaning you design your system in a way that it works on multiple cloud providers because you don't want to be bound to one cloud provider only. Because if you put everything on AWS, then if AWS increases the prices, your business may be down. Also, you are in a much better situation in terms of the risk mitigation and the cost negotiation when you use multiple cloud providers, because you can just negotiate better prices with each cloud provider if you tell them, you know, by the way, I'm also running on AWS and Azure, so GCP, can you give me a better price? And the other reasons are like if you would like to achieve low latency from multiple cloud providers, that's what we did with Hazelcast Cloud. So with Hazelcast Cloud, we designed it in a way it's deployed on multiple. You can choose the underlying cloud provider, because you may want to use Hazelcast from different cloud providers, so you would like to have low latency from any cloud provider. Other reasons are data protection, regulation, compliance, or you build or best fit technology if you build like a heterogeneous environment, so it's not the same every cloud provider, and you would like to use, for example, you would like to use specifically Spanner from Google because you need it. Short summary. So in multi-cloud, there is no vendor lock-in. That is a good thing. You are in way better position in the cloud cost negotiations, and you can achieve low latency if accessed from multi-cloud. From the downsides, the setup is way more complex, and you cannot use cloud-specific toolkit if you use homogeneous environment. Our last level for today, level 5, is hybrid cloud. So hybrid cloud, it means that if all cloud providers are down, your system is still available. They may say, like, really? Is it possible that all cloud providers are down? And obviously, no, it's not possible. So it's not even possible that one cloud provider is hold down all regions. And if all cloud providers are down, usually, I mean, it means the whole internet is down. So there are other reasons for using hybrid cloud. The reason number one, it would be like the data requirements and regulations. For example, you are a big bank and located in Switzerland, and the law, the regulation is that data of your customers, they need to be on your servers, not somewhere in the cloud, not on AWS. They need to be in this building and on these servers. Then you need to set up your at least part of your environment needs to be on premises on your own servers. The other reason is like data security. Some other reason is that you are moving to cloud, so you are on premises right now, and as a phase of moving to the cloud, you build a hybrid cloud environment. And also cost reduction and everything we mentioned in the multi-cloud applies actually here. The diagram for this look like that. So again, we have a global load balancer, which load balances the traffic to your environments on different cloud providers, but also to your environment on your bare metal servers. And you can already see that it's getting super complex. That is why at this point, or even in multi-cloud, you usually need some abstraction layer to reduce the complexity. And this abstraction layer, it can be, nowadays it's usually Kubernetes or some derivatives of Kubernetes like OpenShift or IBM Cloud. I think like that Kubernetes won this war of orchestration techniques, and now Kubernetes is everywhere. But some other popular solutions like the VMware Tanzu, a lot of companies that they use it, like VMware Tanzu is like this former cloud foundry. But I would say like nowadays, like Kubernetes took it all. But you need this abstraction layer because it's just too difficult to maintain different environments at the same time. So a summary for hybrid cloud. So you have no vendor lock-in, no cloud lock-in. You can achieve low latency from any custom network because you can just build your own servers anywhere you want. But your setup is very complex, and you usually need some extra layer like Kubernetes OpenShift, and it costs a fortune. And with the hybrid cloud, we covered all high availability levels. So as a short summary, what I would like to present is like my view, how I see the complexity of the system comparing and the cost comparing to the high availability level that you choose. So I'll draw a graph like this. So you start from a single instance, all good, very simple setup, no problems with anything. You go from a single instance to multi-instance. So suddenly your non-distributed system becomes a distributed system. So you have to think about like data replication and all what comes with this distributed system, like consistency, what with the CAP theorem, with everything what comes with distributed system. Then if you'd like to go from multi-instance to multi-zone, it's pretty straightforward. You just make sure that your tools support zone aware, and that's it. However, if you'd like to go from multi-zone to multi-region, it's another big step, because now you have to cover the long distance. You need to use geo-replication. Your system becomes asynchronous. Your data is asynchronous. It's way more difficult. Then from multi-region to multi-cloud, you cannot use any cloud-specific tools, which is a big deal nowadays. And from multi-cloud to hybrid cloud, it's another big step because you need to maintain your own infrastructure, which is another level of complexity of this whole things. So which high availability level is for me? I would say like that the default one is multi-zone, because in this level you can still have like consistent data and you are very highly available. Obviously you can use single instance if you like risk. I would say that multi-region is for systems that in which you need to go global. You need your system to be accessed from multiple regions. And multi-cloud, hybrid cloud is basically for big enterprises from banking industries with a lot of compliance regulations. That would be this level. And with this slide, I would like to thank you for listening to this talk. It was a pleasure to speak at this conference.